Welcome back to our Python Quickstart tutorial series. Today's topic is object-oriented programming in Python. These topics include the definition of classes, the concept of inheritance, and operator overloading. Welcome back to part 3 of our object-oriented programming. That part is one that I like the best because it gives me most flexibility in my programming. The main concept here is to use classes and to use inheritance as well as operator overloading such that I can create my own numeric data types. So let's start with the basic idea. I want to show you a few concepts and then I look into an example to illustrate the problem. Let's first ask how Python really works behind the scenes with operator overloading. And I do this here as a simple example using floats. So I have example like our first session, A is a number, B is a number. Hey, C is A plus B. Let's plot C. And here we go. It's already quite interesting as a little detail on the side that the result may be surprising to you. 2.3 plus 4.1 is for me 6.4. Why does the computer say it's 6.399999995? The main reason is the floating points are truncations to approximately 16 digits, but it's stored in binary. So it's, as Frank McKenna introduced to you, zeros and ones. Using zeros and ones, you cannot exactly reproduce 2.1 and 2.3 and 4.1, but you create a 16-digit accurate approximation of 2.3 and 4.1. And in our case, it simply turns out that there's about 5 times 10 to the minus 16 or so an error in there. That's floating point calculation. So be it. But at that point, that's what we expect. We found a little extra detail. But what this really does, let's look at this from an object-oriented point of view. Python saying A is 2.3 and B is 4.1 already looks into the 2.3, says, hey, that looks like it's all numbers, has a period in there, it's a floating point number. And what this actually does, it creates this. It creates a float with the value 2.3. Float is a class. So what we are doing here is, this is calling the constructor for the floating point class as float dot underliner init. Self is in the first case the variable a and the value is 2.3. It's calling the constructor. That will remember something. Similar for b. And when I said a plus b, Python looks in this in a different fashion. It says, oh, it starts from the left, a. What type of object am I? And A will identify as float. Then the plus is a short form for a built-in method of the floating point class that's called dot underliner add underliner. That class takes as the first argument, as always, self. Self is A. And the second argument is whatever comes next. That's B. So this is the method that's been executed when you type A plus P. Guess what? There are similar classes or methods for the standard operations. The plus is add. The minus is subtract, so sub. The product is mul. The division is called true division. That's a floating point division. And slash slash is a floor division. That's an integer division. And the percent sign is the leftover. So if you say 3 slash slash 2, 3 over 2 would be 1.5. The floor division gives 1 and 1 left. So it's 3 over 2 is 1 plus 1/2. We have an extra operator, that's a matrix multiplication. That is the operator that NumPy has been using for the dot product or for the various types of tensor on tensor, matrix on matrix operations. That's defined in the matmul, so matrix multiplication tool. Star is calling the power function. And there are many more of those functions. There are functions for comparison. There are binary operators. I highly recommend to look at operator overload in the Python manual. They describe every single available function. Let us explore how these methods can be useful for us and return to an example that we've seen with lists. Remember, we could use lists to look like vectors. Let's do 3D vectors. Let's start with objects that look like a vector. And hey, that's a list, 1, 2, 3. Here's a list, 4, 5, 6. And if you've forgotten about that example, if you add these two, it combines the lists. It is not a vector operation. So what actually happens is that the list class may look like a vector, but the methods do something else. They do set type operations. And we remember that minus isn't even implemented. So I get a type error, unsupported operator type minus. That is one of these error messages implemented in the generic object class in Python. So it's just, if we don't define it, or if a class doesn't define it, that's the default error message. So what we want to do is we want to build a vector class that behaves like a vector. So what I'm looking for is, hey, let's start with a list, because a list looks like a vector. And what we have to do is we have to change the add and subtract such that we can do a vector addition and a vector subtract. The trick works very simple. We define a vector class. A vector class, that means first we need to find a way to create one. We do this by defining the constructor, underliner, underliner, init, underliner, underliner. Standard syntax, it starts with self, and the second argument is now a vector. And we said, let's do a 3D vector. We start with a list. We start with a 3D list. And I use here that trick again. I use a default argument that says, if I create a vector without an argument, I get a 0 vector. Makes kind of sense. If I start a variable, there's nothing. Let's call it a 0 vector. That is a variable that only lives as long as the constructor lives. So we want to remember that. And I simply want to use my vector self.v. I use an uppercase V in here, just random how I pick that one. And I remember it. So at that point, I remember my variable as a list. Then I want to make sure for debugging, I want to be able to print it. So the string function needs to return a string. A list already has a string function, so all I have to do is I call the string method on the list object. That's my list object. That's already implemented, and I return that. So at that point, I can print my vector class. And I use the constructor where I say, hey, how do I construct a vector? By the keyword vector. And I have to put the list its values in a list. So that creates a string type answer. Now comes the interesting part. If I use plus, then we got this behavior up here. The correct vector plus would be first component plus first component of the second, second component of first plus second component of second, third component of first plus third component of second. So let's program that. And it's pretty easy to program that. I simply start here. I initialize a list. And hey, it's a 3D. I do it quick and dirty. We have a for loop over 3 indices. So the range 3 gives me the indices for 3 components, 0, 1, and 2. I is an index, and I simply have the answer. Here is my answer. Component I is self, because add is always called with the first argument is the one left of the plus, and the second argument is the one to the right of the plus. So I have the i's component of the left one plus the i's component of the right one. And once I'm done, I return, but I do not want to return the answer. See that the answer is a list. So if I want to save that and keep working as vectors, the answer should be a vector. So I use the list as an argument in another constructor, and that creates a new vector. It returns a new vector object. There is something special here. WI. That is a vector object. If the second argument is a vector, then how does a vector know what the i's argument is? There is a special method that we have to implement, because that's not automatically trivial. If you create your own data type, you need to say how indexing is supposed to work. And we know that it should be the i's component of my list. The list is self.v. And so what I do, what this does, is it calls vector the get item function. The get item function, that is these brackets, the indexing operator, is the equivalent to the get item function, and says, of yourself, give me the i's component, and you simply return the i's component of my value. So that's calling it from W. That would have been the add method. I can implement subtract. Subtract is a copy, but the only difference is a minus. The multiplication, I just want to use the multiplication as dot product. So a dot product is an accumulative answer. The answer is now a scalar, and the answer is the sum. So I use the plus equal in the range of the i's component of the left times the i's component on the right. And at that point, I have addition, subtraction, dot product, get it by an index, and it may be helpful to modify something. So if I say vector index 2 equals a value, that is similar to the get item, returns the i's element. Set item is something that implements the i's component is a value. So we have an extra value. Looks a bit complicated at first. So our class, if you look at this, in this case, is something where we simply modify the behavior of plus, minus, product, and indexing. And we, in this case, we only store a single list. There could be many of those variables. Let's try. So this was, I just executed it. And now let's go here. I create one vector, 1, 2, 3. I create a second vector, 4, 5, 6. I call them u and v. I have print. I do addition, subtraction, I do the dot product, and to make the test more complete, I create these computations, not just by themselves, but I assign a new value, a new variable. W also should be a vector. We will test this by print and by keep doing further operations. So let's try that. Double check, print U, print V. That's what we expected. U plus V is now component by component, 1 plus 4, 2 by 5, 7, 3 plus 6 is 9. This is the next line, that's U minus V. That's the dot product, 1 times 4 plus 2 times 5 plus 3 times 6. Then I perform W is U plus V, that is silent. And I bring W. So it worked, it behaves like the vector. And W minus V should be U. I print that, it could perform these computations. And again, don't forget, the lists by themselves couldn't do this. Now we have something that behaves like a vector class. Would I implement it that way? Not if I learned NumPy and I figured out that the array class can do all that for me. I used it as an example because it's something that's easy to implement and shows a lot of the issue. Before we conclude this chapter, I want to show you in another short video clip how we could debug these operator overloads.